Right. Hi, everyone. Welcome to the first talk of our new series. And today we have an amazing talk by Jifie Song from the Huawei London Research Center, who will be telling us about human-centric neural rendering, or NeRF. And Jifie, thank you for coming. We're very excited to learn from you. Please, the floor is yours. Go ahead.
Okay. Thank you, Hassan. Thank you for the invitation. Yeah, I'm happy to be here to sharing my thoughts on neural rendering. Yeah. Okay. So let's start. So at first I'll give a basic idea about this neural rendering, and then I'll talk about a few main directions about this neural rendering. Okay. Let's go one by one. So at first, so what is neural rendering, or NeRF? So NeRF here is first proposed by Middlehall and his co-authors on ECV 2020. And since then, it has been progressed very fast. So what NeRF is doing is like this. So NeRF is trying to learn implicit neural representation by integrating this position encoding and also the traditional volumetric rendering all together. So basically, they're using MRP to build this neural reading field, and the input to this MRP is this 5D input, including position and also the view direction thing. And the output will be this every pixel's colors and also density. So by doing this for all the image pixels, you can form the image. So you can have this prediction for the given camera view. And then you apply this rendering loss between this predict image and ground truth image. So you can supervise this NeRF to learn. So this is the basic idea behind. And so this is the result for the NeRF. For example, with NeRF, you can do this no view rendering. You can see it's very high quality and it's very photorealistic. So it's way better than the existing method at that time. So that's why it becomes so popular. So and here it shows that with this ray tracing, we can get the color for each pixel and also the density as well. So since then, NeRF has been applied on many directions. For example, these scene reconstructions and dynamic 4D videos, autonomous driving, or human avatar modeling, or many things like that. So, but however, if you want to apply NeRF directly, there are many issues we need to solve. For example, if we apply the NeRF on this sparse field scenario, for example, we only have, because original NeRF requires these dense field settings, but in many cases, we don't have very dense camera setting. Normally, we only have a few of them, which is sparse field setting. But as you can see from here, this sparse field setting, the NeRF will suffer a lot. And also, NeRF, when the NeRF had been proposed, the NeRF is trying to reconstruct scene for the static scene, which means it couldn't reconstruct the dynamic cases. So that's why for the dynamic cases, NeRF will fail for sure. So for the first situation, when the input view is very sparse, the depth or some other geometry pair can help a lot on this scenario. So that's the topic we want to talk at first, which is depth-based neural rendering, or depth-based NeRF. So at first, let me give a brief literature review on this direction. I mean, this depth-based NeRF. For example, at first, this depth supervised NeRF, as you can see, the NeRF will suffer a lot on reconstruct this plans. But what this paper is doing is that they apply this supervision loss from the depth, like depth camera or something like that. So it can do much better job compared to the NeRF. And after that, they further apply some regularization loss. For example, in this paper, which is trying to regularize this, because, for example, the neighboring pixel, they should have similar color or similar depth. So that's how they apply this to regularize MRP to learn a better job, to do a better job in the sparse view scenario. And also, And also the depths we mentioned in the earlier paper, normally it's very sparse depths because they get the depth, they obtain the depth from the structure from motion. So depth can be very sparse. So the following paper proposed to do a densification on the sparse depths. So they have this dense depths as the input. And this gave a much better prior knowledge for the NeRF. So in the end, also learn much better job compared to the previous method. And another related work is like this one, because this NeRF also has this density. So that means NeRF can also use to reconstruct the 3D scenes. So that's this NeRF RGBD work is doing. They're trying to reconstruct the scene both in geometry and also reconstruct the color as well. So we also have a work on this direction. This is what we have done in CVPR last year. So because we in this field, for example, there are many issues in this field. For example, at first, as I mentioned, in the sparse view setting, we need geometry prayer to help the NeRF learn do a better job. So so that's why we propose this this idea or this pipeline. So so what we did here is that we develop a camera rig, and also we put this camera rig on the robot arm. So for example, as you can see, this camera rig, we have many different sensors, like this RGB sensors, and also TOF sensor, which is also very popular in the robotics, and also this active stereo sensors, which give you stereo depth as well. And also we mounted in the robot arm. This is because normally in the NeRF, we rely on structure from motion to get the camera pose. But some cases, the camera pose is not accurate. But here with robot arm, we can give a perfect data with very accurate camera pose because everything is preset. So with this rig, we can provide a much better data set for this community. As you can see, we have different modalities for multiple sensors. And also we have this very accurate camera pose, which is given or which is known from the robot arm. So basically this is the data acquisition pipeline we are doing. So at first we do the calibration to calibrate both camera and also robot arm. And then we do this data recording so we can collect this multi-model dataset. So we provide not only RGB image, we also provide some depth images like TOF depths or stereo depths or something like that. And after that, we do one further step, which is trying to using a 3D scanner to scanning all the objects. And with that, we can get very high quality mesh. And then we project this mesh back into the scene. So because this mesh is in high quality, so after the projection, all the depths is also very high quality. So this gives a way better quality depth ground truth compared to all the existing sensors. And also because we know different objects, so this also gives us a semantic label as well. So in the end, this dataset gives us very much better depth than all the existing sensors. And also at the same time, we have the semantic label as well because we scanning different objects separately. And with this dataset, we can do a much better depth-based NeRF or depth-based neural rendering. So as you can see, compared to RGB only, the NeRF is failed to render the scene in a correct way, and also geometry is very messy. And with different sensors, this quality can be improved a bit. And with the depth we provided, we can get the best depth compared to all the methods here. Yeah, so this is what we do in the CVPR last year.
Jifie, can I ask a question maybe?
Yeah, feel free.
So just to understand this experimental result, so the row on the bottom is what we reconstruct with NeRF?
Yes, both first row and the second row are reconstructed by NeRF.
Right. Okay, but one with your data, which has this multiple inputs, multiple type of sensors, and another with just one of those data, like RGB, active, stereo, or I2F or LiDAR, right?
Yes, yes. The first
Okay,
one, RGB only. Yeah.
okay, got you. Okay, thanks.
Yeah, thank you. So yeah, basically, so here in this work, we contribute a much better dataset to support this depth-based neural rendering, because our dataset can provide you much better depth and also much better camera pose. So yeah, we think this is very helpful to the community. After that, so another topic I want to talk about is this dynamic neural rendering, or more human-related neural rendering, because we are also working on 3D digital human last year. Yeah. So compared to the static thing, so the dynamic thing will be much more complex, because we need to model the dynamics as well. For example, as you can see from here. So this is work from Meta, and with NeRF only, it will be very hard. No way for NeRF to model dynamic thing for sure. But here, because they introduced this dynamic NeRF to encode the time into the MRP, so it's possible to separate this thing. They model this dynamic stuff and static stuff separately, and then they blend the two things together to output the final thing like this. So this is the rendering. This is the final rendering. Yeah. But the drawback for this paper is it's super time consuming, which is reasonable, because with the MRP to model the dynamics and to memorize that, it takes so much time to learn and to render. Yeah. So and also more specifically for the human related thing. So and before we go into our work, I also want to briefly introducing the literature review for this field. For example, this neural body, I think it can be viewed as one of the first beginning work working on this human-related nerve. So what they are doing here is that they using the prior from the sample, which is the human morphable model here, and they extract using the sample fitting and get the vortices from there, and then they learn this. Then they obtain this latent code here, and then they pass through this sparse-com net to get this neural volume for this body. And then with this neural volume, they can do the same thing like the NeRF is doing, like volume rendering to get the density and the color. So, and this is the result they get. So you can see they can model and the human and render the human well with their method, because human is dynamic, but they still can manage to do it. So it's worked 3 years ago, but it's quite nice at that time. So to model the human with neural rendering, it's super cool. Yeah. And after this work, or actually this work is a kind of concurrent work with that one. So this one, what they are doing here is that they also they treat they build the human, they model the human in canonical space, and in this canonical space they view human as static, and then given any dynamic frame, they trying to map the observation space into the that canonical space. For example, they using this skeleton model to trying to connect the two human. For example, the human within the any given arbitrary time into this human in the canonical space. And then after you mapped into this canonical space, the human is static, which means you can using the original NeRF to render this human out. So basically this method is trying to separate this task into two things. One thing is this mapping thing or deformation thing. And after this deformation, you have this canonical space. And with this canonical space, you can render directly with the NeRF. So yeah, and then you can render any dynamic human using this method, like you see from here. But as you can see, the drawback is for sure the quality is very low. You can see the human not looking very nice here. So after this work, so this human NeRF is trying to improve the issues we mentioned there. So for example, what they are doing there is, again, is trying to mapping this, again, trying to building a canonical neural volume for this human. And then they also have this deformation module, which they call it skeleton motion, and also this non-rigid motion. The skeleton motion using similarly, using the prior from the sample to deform the human given a body pose, given input body pose. But at the same time, they're arguing that, for example, the clothes in the human is not rigid, not moving in a rigid way. So that's why they have this non-rigid motion module to model the movement from the clothing or some other part like skin part. So they have these two things combined together. They have this rigid motion and this non-rigid motion all together to model all the motions. And after that, after this all the motion field had been obtained, had been computed. So again, this human will be mapped into this canonical space. As you can see from here, this lady in the T pose is the canonical space they define here. And then they just go through a MRP in the static NeRF to get the color and the density. So yeah, as you can see, the result from here is much better than the previous methods. Yeah. Yeah, so it's quite cool. They can do this free view rendering, free view rendering for any given human avatar. And apart from a human body, so there is also human head, because human head is very important. For example, in digital human, normally, if we are talking to a digital human, this talking head will be very important. I mean, all people's attention will focus on the talking head part. So that's why they have this, people also interested using NeRF to reconstruct the talking head. For example, in this work, which called this NeRF blend shape. So they're trying to get the different basic features from existing head morphable model, like here. So they learn many basic features, and also given a face feature from a new pose, they are trying to represent this new feature using all the basic features, and with this you have a final feature vector by multiply this all the basic together, and with this feature vector, so you can do the same thing like volume rendering to get the color and also the density. So this method is very fast because it's based on instant NGP. Instant NGP is another work based from instant NGP is another famous work from NVIDIA. So they really speed up this NeRF training from probably 10 hours to 10 minutes. So it's quite fabulous. So here it's based on instant NGP. So that's why they can do this talking head reconstruction in 10 minutes to 15 minutes. And the result also looks quite good. So you can see compared to the baseline method like neural head avatar or NeRF, yeah, their method can do a better job. And also they can do much faster. They can do much faster compared to the baseline alternatives. And also, for example, in this work, which is point avatar, so they further introduces geometry information like 3D geometry information like normals, because with normals you can process lighting much better in a better way. For example, like here they introduce this shading network, and when they are normal, when they reconstruct this face, they also estimated the normals, and with the normals, and you can relighting the faces, so it looks more realistic. And yeah, as you can see, the reconstructed head is looking more visually better because they also processing the light, model light here. And this one is also very fast because it's point-based rendering. So, and also hand. So similarly, they also have this hand nerve trying to using this hand deformation model to model the hand. So we also have a work here. So we also have a work in this field. So here, we present this hand-object nerve, trying to model this hand-object interaction. So this work has been accepted in 3DV this year at Spotlight. So what we are doing here is trying to model this grasping process. For example, we are trying to grasp some object, and we are using this nerve to reconstruct the whole process. So specifically, so at first we model this hand. We have this, we're using the nerve to model this hand. So as you can see from here, we have this hand deformation field. So again, we have this skeleton motion and also non-rigid motion. So we can reconstruct the hand in a very nice way, and given the hand pose. And also we have this object. We also model this object using another nerve called object nerve. And object will be much simpler in the hand case, because object normally we treat as a rigid motion here. So we treat it as a rigid object. So we only consider rigid motion here. And also we form, and also we apply this contact constraints, because when we try to grasp this object, for sure there will be some prior knowledge like this contactness. So that's why we further apply the contact constraints to make sure that hand contacted with the object here in a nice way. So with all the modules together, we can our method can model this hand object well. And as you can see, compared to the baseline method, we can do a much better job in this hand object reconstruction scenarios. And for example, given this multi-view videos for grasping scenario, we can reconstruct this grasping this scissors in a much better quality compared to the baseline method. And here it's a multi-view setting, for example, 3 or 4 cameras. But when I talked to Hassan said he don't like this multi-view camera settings. So yeah, but fine. Our method also supports this monocular view settings. Yeah, for example, we only have 1 camera, and yeah, still we can do a good job. So yeah, you can see compared to the baseline method, we can reconstruct this grasping scenario well. Yeah, so yeah, it's fine. I mean, even in the even when only 1 camera is given, we can still do a good job here. So yeah, this is what we did in this field, and it will be appearing in 3DV this year. And in the end, I also want to mention this 3D Gaussian splatting, because this field is progressing too fast. So, and the 3D Gaussian splatting, and you may know already, I mean, this can do a much quicker job. For example, as you can see from here, compared to the SOTA nerve, this can be trained in just a few minutes. But previous nerve like this mid nerve, it will take 2 days to train. And also the inference time is like 100 plus FPS. It's just amazing. So we are so lucky to witness this paper had been published, and this paper has also been awarded as the best paper in SIGGRAPH. So now now in this field, many people working on this 3D Gaussian splatting and also related tasks. So for example, we have seen many papers using 3D Gaussian splatting to solve different 3D tasks like scene construction and like human modeling, like scene editing, like scene generation, like yeah, many 3D related tasks. Before they are trying to using NeRF to solve this task, but now I think there is a trend that people are using 3D Gaussian splatting to solve this task. I mean, where they can achieve a better quality, and also they can do in a much faster, in a much faster process. However, I mean, this doesn't mean that we shouldn't stop working on the NeRF. I mean, because NeRF still have its, I mean, strengths. For example, NeRF is very small, like NeRF normally built by MLP, and also Google is still trying to push the boundary for NeRF. For example, I remember John Barry had published this NeRF paper recently, which they can do a very fast neural rendering using NeRF. I think the speed will be similar like 3D Gaussian splatting. So I think there will be a debate which will be better, like this NeRF is better or 3D Gaussian splatting is better. So I'll put a question mark for this question. So let's see how this field will go in the end. Yeah. So okay, so let me conclude the talk I gave today. So I mainly covered two directions here. For example, the first direction is this depth-based NeRF. And the take-home message for this depth-based NeRF is that this depth regularization is a very important key here to help in this spatial setting. And also with this geometry pair like depths or normals or something like that, normally it can help with the much better quality rendering, especially in this spatial setting. And also it can accelerate this NeRF training. So that's why probably in this autonomous driving tasks, when you further introduce depth signal from LiDAR or from other depth sensors, it will help a lot. And another direction we talked today is this human-centric NeRF. So for this human-centric NeRF, as we mentioned that static NeRF will fail to model these dynamic things, especially, for example, this human rendering or dynamic human or talking head or something like that. So to address this, so what people normally doing is that people building a deformation module to cover this deformation part or dynamic part. And the deformation module normally is based on some prior deformation model, like, for example, simple model for human body, or flame model for the head, or matter model for the hand. Yeah. So yeah, all this prior knowledge will help on this human-centric neural rendering. Yeah. So yeah. So that's it. Yeah. Thank you. Yeah.
Thank you so much, Jifie. This was very, very interesting. And actually, I want to apologize to our viewers because there were some Zoom pop-ups happening because of the unlimited access, which I already managed. So yeah, apologies for that. I do have some questions, if you don't mind. We can have a discussion.
Yeah, feel free.
That's okay. Yeah. So I mean, where do you see the application of NeRF being very useful? Like, do you think there might be any connection between NeRF and robotics, for example, that we could exploit? So I see that you already, used a robot to collect data for NeRF, right? But is there a way where like 3D reconstruction can help a robot somehow, for example?
Yeah, I think so. I think this so I think this NeRF and robotics, they are a good friend, because NeRF can help the robotics to understand the 3D world, and robotics can further with NeRF can make the actions and make NeRF to do some real applications. So I think NeRF and robotics can be a very good friend with each other. Yeah.
Right. I see. Interesting. And so what do you think is the biggest remaining challenge for NeRF that we should actually all look into as a research community? Where do you think this technology should go next?
Oh, yeah. So right now, this 3D Gaussian splatting really pushed the boundary for the neural rendering, because previously the pinpoint for this NeRF is that the training is so long and the inference so taking so much time. But not right now, this 3D Gaussian splatting really is solving this. And for example, they can do the training and the testing very fast, but it's still not perfect. For example, compared to this MLP-based NeRF approach, this Gaussian splatting takes a lot of space.
Mm.
So it's very heavy compared to the MRP, compared to the MRP or compared to NeRF. So people is already working on this. They're trying to propose some smaller Gaussian splatting like this light Gaussian, but there are still some work to do on this. So
Yeah, I see. And yeah, one more question, if that's okay. So in what you discussed, it seems that NeRF is still relying on MLP, the neural networks. Is that fair to say? Multi-layer perceptrons? Is that...
For 3D Gaussian splatting, actually, it's not using MRP. It's more like a implicit representation.
Yeah, but I mean the previous NeRFs ones you discussed.
Oh, yes, you're right. You're absolutely right, yes.
And why is it MLP and not a transformer, for example?
So I think MRP here, because when you're trying to using an implicit representation, you want this thing to be very small and very compressed. And with MRP and also the position encoding, it's already enough to present the whole thing. I mean, there's no need to put transformer there. For sure, transformer can further, for example, bring more information, and it has much larger capacity. But here, I think, the researcher had shown that MRP is enough to model this whole thing. So
Right.
That's why they take MRP, which is much lighter. Yeah.
Right. I see your point. Okay. Yeah. So transformers is not always the answer, right? We have to pick the right model for our problem, right?
Yeah. MRP here is good enough. Yeah.
I see. Okay,
Yeah.
very interesting. And one more question. So there are certain situations. Imagine we are dealing with a scene, that is dynamically evolving, right? There's typically physics constraints that we need to take into account, right? How would we introduce some physics constraints inside a NeRF model, for example? Because like there are things, maybe this will restrict the search space or help search faster, or what do you actually think about this?
So I think it doesn't conflict with the NeRF idea. For example, this physics thing in normally like, for example, if you have this mesh, or if you have some other thing physics related, so they can do this a collision detection or something like that. So this can be combined together. Actually, there is already something work in this direction already. For example, I think Jiajun group from MIT, they have proposed this object NeRF. So they're trying to they build this SDF and also other object intrinsic information into the NeRF to help with the simulation. And also latest 3D Gaussian, like this physics Gaussian, they also introduce this physics into the 3D Gaussian. So they are making this thing happen. Yeah.
I see. Okay, got you. Yeah, I also know we have other audience here. So Zaf is here. Zaf, do you have any questions you would like to discuss with Jifie?
Yeah, actually, I just want to ask a couple of very basic things. Thanks for your talk.
Thanks, Zaf.
As well. I think it was very interesting and impressive work. Very good to know. I was wondering regarding this human-centric approach, similar to Python, but from a little bit different perspective. Do you think that the field will find a way to create any kind of objects, not just human?
I think I'm lost in.
Yeah, I think Zaf, you might have a connection issue. Actually, we cannot hear you well.
Human parts that depending on the type of object. Sorry.
Yeah, I mean, would you mind typing your question in the chat? I will ask it to Jifie because we cannot hear you well because of internet connection. Yeah. So I mean, as Zaf is typing, right? So do you think we could ever combine because now the way you collect data, is it passive? Is it fair to say it's passive the way we collect data, like you position your cameras in certain places and so on, right? Is that fair to say? Okay.
Yeah,
So
yeah.
do you think it's possible to actually collect the data in an active way? Like if
Yeah.
yeah,
Yeah, I actually really like the idea of when we discussed, I mean, in the first beginning, I think in the first meeting, we discussed this, yeah, for example, if we can using this our policy to help the NeRF to collect the best view angle or viewpoint, yeah, I think that would be very cool. Yeah,
right.
I think
I see.
there is some work already, but we on this direction, but we can still trying to work something out here. I think it will be very cool. Yeah.
Right, I see. Okay, cool. So I think, yeah, Zaf just wrote me the question, so I can actually ask you that. So he said that he has a similar question to mine, but from a little bit different perspective, right? So he's saying he's wondering regarding the human-centric approach to NeRF that you mentioned, right? Do you think the field will find a way to create general dynamic priors for any kind of objects, not just the humans and the human parts?
Oh, yes, yes. I mean, there's some work working on this. So what they are doing is, for example, they're using another MRP, like time-based MRP, or some other or flow-based MRP. So with this MRP, they are trying to model the dynamics in this scene in a general way, and also they're trying to border prior knowledge, for example, from optical flow or scene flow to help the NeRF to learn this deformation thing or dynamic thing in the scene. Yeah.
I see. I see. Okay, one more question from Zaf. So in other
Yeah.
ML fields, we have a clear threshold beyond which we say that this becomes a solved problem, right? So in machine learning, we say, okay, if I get an accuracy above that amount of time for that amount of accuracy, then I say the problem is solved, right? For example, in automatic speech recognition, once we understand all the human speech, kind of it's considered a solved problem. But he's saying that it's hard to see a limit here where we say the NeRF problem has actually been solved, right? So how would we decide? How would we decide? Okay, this is where the NeRF problem is solved, and we should now jump and pay attention to something else.
So I think so NeRF here is just a representation, and it's used to solve different tasks. So it really depends on all the downstream tasks, for example, autonomous driving or 3D scene reconstruction. So with this representation, and if this representation is good enough and it helps the downstream task to solve in a very good way, then we can stop on that downstream task. But NeRF as a representation, we can also try to improve this representation. Yeah. It will be beneficial to all the downstream tasks. Yeah.
I see. And as far as you know, is there any foundational model for NeRF? Like, does there exist a big model for NeRF that
Yeah.
people?
So there is some big model for generalized NeRF. For example, put one image in, and then you can try to generalize this 3D neural radiance field. Yeah, there are some model like that, which is a trained down very large data and the big model. Yeah.
I see. Okay.
But normally the NeRF we say is kind of scene based, I mean per scene based. But we do have this generalized NeRF. Yeah.
Got it. Okay. Okay. Understood. Awesome. Okay. So, Jifie, thank you so much again. I think this was a fantastic start to our series. So with that, I would like to end the video. Thank you all for watching. Please make sure to like and subscribe if you found this series very useful. Please comment on the video if you have any questions. Jifie, myself will try to help answer them. And if you have any further questions or you would like to collaborate with Jifie, please let us know, and then we'll get you in contact to try to see these potential opportunities. Right. So thanks again, Jifie, and see you soon in another series. Thank you.
Thank you. Thank you, guys.
Thank you.
Bye-bye.
Bye.